In this video, we're going to show that if n is composite and bigger than 4, then n must divide n minus 1 factorial. Now, just have two comments to make. One, you subscribe to my channel if you like seeing mathematical proofs done all the time. Hit the like button, leave a comment, subscribe. And the other comment I want to make is, let's look at the first few numbers, first few integers. Well, 1 is not composite, 2 is not composite, 3 is not composite, 4 is, 5 is not composite, and then there's many composite numbers from 6 on. I'm not saying every number bigger than 6 is composite. 7 isn't. So why did they say n is bigger than 4? Why not say n is greater than or equal to 5, or n is bigger than 5, or n is greater than or equal to 6? Any one of these implies the first composite number is 6. Well, they just wanted to say, hey everyone, we're not including the first composite number. At least that's what I take from this. I can't say what the author was thinking when they wrote up this theorem, but that's my take on it. They just wanted to say really clearly, you know everyone, we're gonna rule out the first composite number. Okay, so I'm going to do this by two cases, where case 1 is n is not a perfect square for some integer k, and case number 2, of course, will be n is a perfect square. Okay. So now, if n is not k squared and it's composite, that implies n is equal to p times q, where p is less than q, p is less than n, q is less than n. Like, you know, if this number is more than n, and that's an integer, prime or not, well, they're not necessarily prime. If this number is bigger than n, and this is a positive integer, this will be more than n, so it can't equal n. Same argument with q. Q must be less than n. And since it's not a perfect square, n is not a perfect square, q and n are not equal to one another. Q and n are not equal to one another. Well, p is less than n, q is less than n, and they're not the same number. So p or n equals pq will divide n minus 1 factorial, because n minus 1 factorial is n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Let me say one more thing. Without loss of generality, say p is the bigger one. They're not equal, so one is bigger than the other. Just keep in mind that this here, so let me say if and only if n is equal to pq divides, I'm just going to write this a little bit differently. It's n minus 1 times n minus 2, and eventually p, then eventually q, then eventually 3 times 2 times 1. And here, pq divides this, because p and q are factors of it. Okay, now suppose that n is equal to k squared. The problem here is you can't have k and k, because each one of these numbers are different than one another. Okay, so we know that n is equal to k squared, and I maintain that that's less than 2 times k. Well, let me just emphasize that k squared is k times k. So on the other side, I'm going to put k, and I'm going to put something smaller than k on the right side. That's going to make the left side larger. N is bigger than 2k. That is, 2k is less than 1. And 2k is not equal to k. So n divides n minus 1 factorial, since n divides n times n minus 1 times n minus 2. Eventually, since n, in particular, 2k is less than k. So if n is positive, k is in the positive integers. Let me say that up here too. Eventually, you'll get to 2k. 2k is bigger than k. And eventually, you'll get to k, and eventually you'll get down to 1. Okay, so just want to say one thing, or change one thing. N, which is equal to k squared, it divides this, since k squared divides this. There it is. That is, this times all of that, times all of that, times k squared. This here is a multiple of k squared. Two products, two factors. Well, you can think of 2k here as 2 times k. So k and k, better known as k squared, is a factor of this. It are two numbers in that product. So k squared is going to divide it. This completes the proof. Once again, if you like videos like this, where I prove theorems, subscribe to my channel.